So we've looked at redshift as providing evidence for the Big Bang theory, but what other evidence is there for the Big Bang theory? And that's what we're going to explore next. There is one more piece of evidence that you need to be familiar with for the IGCSE physics specification, and it's called the cosmic microwave background radiation. Now, in 1946, two astronomers built this telescope here that you can see, and they used it to detect signals coming from space, and they realized that they were detecting a signal wherever they pointed the telescope, and it seemed to be coming from all over the sky. Now, they didn't think that this was possible, so they thought there was some fault with the equipment, or they'd installed it incorrectly. But what they then came to eventually realize was that they were detecting radiation. This was real. There was nothing wrong with their equipment, and it was radiation that was spread throughout the universe. And where this radiation came from, it was left over from the Big Bang, and it's called the cosmic microwave background radiation. And what I'm going to explain next is where this radiation came from in the first place, and why it's still with us today. So where did this background radiation come from? Well, when the Big Bang occurred, one of the first things to be created were the simplest particles. So before we had planets, before we had stars, we had to have what they're made up of being created first. So the first thing was protons, positive charges, and electrons, the negative charges. Now, you will have studied that when we put protons together with electrons, they form atoms, but the early universe was very hot, and these particles had enough energy to overcome joining each other to form atoms, and they whizzed around as single particles on their own, and we call this a plasma. When we have positive and negative charges, protons and electrons, and they don't join together, we call that a plasma. And they were exchanging waves between them, like that. So that's what the early universe looked like: positive and negative charges exchanging waves of energy. So as the universe cooled, the positive and negative charges, protons and electrons, lost their energy and joined together to form atoms. So positives are attracted to negatives, and the first atoms were formed, just like you can see on the screen at the moment. And some of you might recognize this atom: one proton and one electron is the hydrogen atom. So in terms of the universe, hydrogen was the first atom to be formed, and you would expect that because hydrogen is the simplest atom on the simplest element, I should say, on the periodic table. So hydrogen was formed first, but what that meant was that these waves of energy that were being transferred between the positives and negatives were no longer being transferred between them, and so we use the expression that they became transparent to the universe. So this radiation, which was no longer being exchanged between the protons and electrons, was just free to roam around, I suppose you could say. And these waves, this radiation, as the universe expanded, this radiation expanded with it, and it got longer, and it got longer, and it got longer as the universe expanded. And we call this radiation microwave radiation, and it's in the universe. Wherever we look, we can detect this radiation, and so we've given it a name, the cosmic microwave background radiation. So the fact that it is there wherever we look in the universe, there must be a reason for it, and our theory suggests that it is leftover radiation from when the Big Bang occurred. And as the universe has expanded, this radiation, these waves have expanded with it, and they're called microwaves. So the name for this background, this radiation, is called the cosmic microwave background radiation. So that is our second piece of evidence. We've got redshift showing that galaxies are moving away from us, and this cosmic microwave background radiation, and there must be an explanation for it. And as I said, the explanation is that it's left over from the Big Bang itself. And so what physicists have done is they have mapped out this radiation to show its strength in the universe, and you can see a map of this radiation in the universe. If it's red, it's much stronger, and if it's blue or lighter blue, it's less strength. So it's mapping out the radiation. This diagram that you see maps out the radiation throughout the whole of the universe, and it is varying in strength, but it is there wherever we look. And so it is another piece of evidence for the Big Bang Theory, or to support the Big Bang Theory. So to complete this module on astrophysics, I just wanted to talk about a little bit of extra information which is not on the specification, but you might be interested to know of other theories. We've got the Big Bang Theory, that the universe started with a bang and galaxies were created and it's expanding. But the steady state theory was suggested in 1948, which is a different theory, and you can see here it suggests that the universe has always existed and is expanding, and new matter is being created as the universe expands. So this is what steady state theory says. The universe has always existed, but new galaxies are being created all the time. And this is an interesting theory. It's a different way of looking at it. So it does support the redshift idea in terms of saying the universe is expanding, but there is a new idea that new galaxies are being made all the time. And there are various theories about what will happen to the universe, and on the right hand side you can see the graph that shows two of these ideas, and this is where we are at the moment. So just marking that on there. Okay, so the x-axis is time, and the y-axis is the size of the universe. So from the Big Bang to now is 13.8 billion years. But what might happen? So it could be a case that the universe carries on expanding, and that's called the big yawn, that the universe is getting wider and wider. Okay, or it could be a case that we collapse back in on ourselves, and that's called the big crunch, or we stay at a steady size. So there are various ideas as to what may happen to the universe, and we have the evidence to show that the universe is expanding, but what comes in the future we're not really sure. And the final thing, taking us to a really exciting area of physics, is that yes, the evidence does show the universe is expanding, But in reality, according to our calculations, gravity should have collapsed the universe. And we believe that there's something there that we can't see that is driving the universe to expand. And because we can't see it, we've called it dark matter. And there are some strong ideas as to what dark matter actually is. But a really interesting, fascinating area of physics in terms of exploring what is a relatively unknown area. So that brings us to the end of the Astrophysics unit, and you will then need to go back to the assignment after you've watched this video to follow the instructions there as to what you have to do once you've watched this final video. But I hope you've enjoyed the Astrophysics unit, some of the most exciting areas in physics, and we do follow this on at A-level in year 13. But any questions about this area, especially this area of dark matter, do field them to me and we can discuss them. Thank you.